Hey everybody, tonight's notes are on reaction rates. Reactions, by reactions I mean chemical reactions with chemicals. And by rates, rate is a synonym for speeds. So tonight's notes are on the speed of chemical reactions. So the speed at which a chemical reaction occurs. Here we go. All right, so this is our collision theory. This is the theory, collision. This is the collision theory. You know how we had our kinetic molecular theory that gas laws were based off of? Chemical reactions are based off of this collision theory. So the collision theory states that in chemical reactions, chemical bonds are reorganized. And here's the three requirements for a chemical reaction to occur. Molecules have to collide, so they have to touch each other. They have to crash into one another. That's the first requirement. With enough energy, so with the right amount of energy, that's the second requirement, to break old bonds and form new ones. The third requirement right here is the molecules have to collide in the right direction. So by direction, it's kind of like if your goal is to hook the front bumper of your car to someone else's rear bumper. In order to make that happen, you need to crash into the back end of the other car. So the collision has to occur with enough energy to hook the bumpers, and your front bumper has to hit their back bumper in order for that reaction to occur. So that's the three requirements. Collisions with enough energy and in the right direction. Here we have a graph of the energy that's required. And the energy that's been required for chemical reactions has been measured for a lot of different reactions. In order for the reaction to occur, the amount of energy is the activation energy right here. The amount of energy, the reactants are going to need some energy in order to get up to the top of this hill so that they can react and form the products. Draw this graph in your notes. Make sure you label it. It does come into play a little bit later on in these notes. All right, so these notes, we're going to go through all of these different variables in chemical reactions. What I want you to do is write down each one and skip 2 lines between each of these. Pause the video until you've written it down and with the 2 lines skipped. So first we've got the effect of concentration. Concentration relates to the amount of stuff present. And here's what you should write down on your 2 lines. If you've got more stuff, you'll have a faster reaction. So if we go back to that car crash where we want to hook the front bumper of one car to the rear bumper of another car, if we only have 2 cars on the entire planet, we have a very low concentration, a very low amount of stuff present. It's going to be hard to do that reaction. That reaction is going to take a long time in order to get those 2 cars to meet with the right amount of energy and in the right direction. Now, if you go and have like 10 million cars in a small amount of space, then you have increased the concentration of cars around by a lot. And you'll be able to make that reaction to occur very quickly. Because in this case we're talking about cars, but if we go back to chemicals, the chemicals are more likely to find each other and collide with enough energy in order to change the bonds. An example with chemicals is our 6 molar hydrochloric acid reacts with a greater rate, reacts faster than 3 molar hydrochloric acid, because 6 molar hydrochloric acid is twice as concentrated. If we see a graph about a reaction happening, so notice we've got time on our x-axis, amount of product on our y-axis, so this would be the cars after they've collided, or this hydrochloric acid reaction after it's gone, we find that we get initially very little product, and then our amount of product flatlines. Now, initially, we don't have very much product present because we have all reactants. So here we have all reactants. As the reactants react, they do form products at a steady rate until here it flatlines, and it looks like the reaction stops. It actually does stop because here we have all product. That's the maximum amount of product that could be formed given this original amount of reactants, and it will flatline because all the product is formed, and once all the product has been formed, we can't form anymore. And that's the deal with this graph. Here we go. Next is number of moles. The number of moles is going to be the same effect as the higher concentration because moles also relates to amounts of stuff. And if we have 100 million cars, they will crash more often and in the right direction than 2 cars. So if we increase the number of moles, we'll have more stuff around, and that'll make a faster reaction because, so here's the reason, the chemicals are more likely to find each other and collide with enough energy to change bonds and in the right direction. All right, next we've got time. The initial or the starting reaction rates are always the fastest. So the starting reaction rates will always be the fastest. The reason why is that's when we have the most reactants around. So that's when we have the highest number of reactants present, the highest amount of starting materials there. So the collisions are more likely because the chemicals will find each other and collide with the right amount of energy and in the right direction. As time goes by, the rate slows because the reactants are being used up. The amount of stuff decreases, so the reaction rate seems to slow. We can look at the same graph that we looked at from before, but this is going to tell us something different now. The slope of the line, or the way that the line's curved, is equal to the rate of the reaction. Notice that here in the beginning, the slope is very steep. That means that we have a very fast reaction initially. Here in the middle of the graph, the slope is very shallow. That means that we have a slower reaction going on. So reactions slow down, start off fast, then they slow down, and yeah, they actually do eventually stop. Right here, it's stopping. Why? Because all of the reactants used up. The reaction rate becomes 0 because we've flatlined, because all of the product that's going to form has formed. Next we have temperature, and usually a higher temperature will mean a higher reaction rate. The reason, and this is what you need to write down in your 2 skipped lines, the reason why is because if we heat up something, the particles have more kinetic energy. The particles move faster. That's what we're highlighting right here, is that the particles are moving faster. If the particles are moving faster, then they hit each other more often with greater energy, so the rate will be faster. if they're hitting each other more often, it's more likely that they will hit each other in the right direction. And that's how temperature affects reaction rates. With surface area, the more surface area you have, the higher reaction rate you'll get. So that means, what that means to us in practical terms is if we've got a solid, we're going to need to break that solid up. We can't use an intact solid in a chemical reaction and expect it to go quickly, because only the surfaces of that solid will actually react. So our practical example is if we're doing a chemical reaction with sugar, we're not going to use the sugar cubes. That has less surface area. Than something like superfine baker sugar or even normal crystal sugar. Superfine baker sugar is kind of like powdered sugar, but powdered sugar has cornstarch added in to make it all powdery. Superfine baker sugar is if you like grind up regular sugar, that's what you'll get for superfine baker sugar. It's used in candy making, and it will have more surface area. The more surface area you have, the faster your reaction will go. And this is for solids only, because only the surfaces of a solid will react. Only surfaces of solids react. The middle of the solid can't react because the other reactant can't get into the middle. Next we've got pressure. So pressure is only affects gases. If you've got a solid and liquid chemical reaction going, pressure will not affect the rate or the speed of that chemical reaction. Pressure only affects chemical reactions where gases are one of the participants. It could be a product, it could be a reactant. It has to be present, though, in order for pressure to affect the reaction rate. The deal is, more pressure will make a higher reaction rate. Why? Because when gases are under pressure, they move faster. If the particles are moving faster, they'll collide more often with greater energy. And again, pressure will not matter if all of the substances are liquids or solids. Something has to be a gas. So pressure matters with gases. The phases of substance will also help you increase or decrease your rate of reaction. If you break up your solids into small pieces, you increase the surface area, and more surface area means a faster reaction. Liquids react the most effectively because we have the smallest particles in the smallest amount of space. Gases will react the best with high pressure because theoretically we'd be compressing them down, making them move faster, making collisions, forcing collisions to happen more often. Last, we've got a catalyst. And how a catalyst affects the reaction rate is by lowering the activation energy needed for a reaction to get started. For this slide, you need to write down all of this whole thing, including the graph, because the graph describes what we mean by lowering the activation energy. So that first graph you drew, the activation energy went all the way from top to bottom of the hump. When we have a catalyst, we lower the activation energy. The blue line, that's the lowered activation energy. So less activation energy means the reactants need less energy to get over this hump. So here's our reactants, and they're starting off with this amount of energy. When we have a catalyst present, we need less energy to get to the top of the hill so we can form our products. Some facts about catalysts, just a reminder from biology. Catalysts are not used up in chemical reactions. What they do is they help with the orientation or grabbing of molecules. So they'll really affect the direction in order to make the reaction go faster and use less energy in the process. So it would be kind of like our catalyst in our car crash example would be if we had some giant kind of device to line up the cars and make the cars all nice and in line, bumper to bumper, so that when they did hit each other, they'd be hitting each other in the right direction. Some catalysts can even give energy to give the activation energy to the reaction in order to make it go. So, if a reaction only goes forward, then the reaction rate will be increased when a catalyst is present. However, some reactions are reversible. And that's what we're getting to in this unit, is reactions that go backwards. And what happens in that instance when the reaction does go backwards. So that's what's coming up in notes tomorrow, and notes for tonight are done. Congratulations.